Okay, so we have already done week 1 to 5 already. So we are starting with neural network fundamentals, right? And then we will look at optimization and training dynamics for neural networks. When it comes to neural networks, especially deep neural networks, a bunch of things begin to become more important when it comes to optimization and training. Then we'll look at some special types of neural network architectures. So the convolutional neural network is one of them. The basic neural network architecture is, a feed-forward network, or what we call a dense network, a densely connected or fully connected network. But then we have others. A sequence model are what we call recurrent neural networks. So these are networks that kind of keep track of previous things that happened, previous events, right? And this is needed in areas like natural language processing, time series processing, and other kinds of things. Then we will now talk about the more modern architectures, starting with attention mechanism that leads to the transformer architecture, which is what the modern large language models are based on. They're based on transformers. And transformers are basically a recent architecture. Well, not too recent. It was in 2018, 2017 or thereabouts that a group of Google researchers discovered this after doing a bunch of research. So it's kind of a sequence, it mimics a sequence model. I wouldn't say it's a sequence model or a recurrent neural network model, but it kind of mimics it and allows you to train at scale and in parallel. So that is immediately transformers came on the scene. Um, Recurrent neural networks kind of died off a bit, and the applications when recurrent neural networks were best at, transformers became better. So applications like natural language processing and things like that. Then after that, we talk about large language models, which is the modern day LLMs. The large language models are based on the transformer architecture, and we'll see how they work. And we may do a bit of training. We'll also learn how to train it. So when it comes to neural networks in general, there are a lot of moving parts, a lot of things that are very key to know. And it's not just about knowing what architecture, but even knowing how to train, even knowing what hyperparameters to choose. This everything becomes very critical, every little thing. Then we talk about generative models. So generative models are basically based again on the transformers. It's the same kind of thing, right? But a generative model is a model that you train to be able to generate content. So we have GANs, we have um, diffusion models, and all of that. And then we'll do a little bit of reinforcement learning, which we cannot really cover. Reinforcement learning is a totally other, whole different field of study. But we'll just do a little bit of introduction, and then we'll also look at what I call ML ops, the aspect of machine learning that a lot of people don't even know about, which is how do you scale up, right? How do you after training all these models, how do you deploy them and how do you keep them running with the high demand that the whole world today is making on machine learning models? Okay, so we are starting off with an introduction to neural networks. And so for this week, we will look at basically right from the basics of neural networks, how they work internally, internal representation, um, the history of it, right? And then we will also look at the mathematical model of a neuron, of a layer, and of the entire neural network. And we'll talk about some of the interesting and key innovations that led to the current dominance of neural networks as the most successful machine learning model architecture in the world today, right? Um, so neural networks have basically facilitated everything that we are now able to do with machine learning or with AI. And then we'll do a little bit of PyTorch. So we are going to do most of the hands-on on Thursday, but today we will just maybe look a little bit at PyTorch. So when it comes to neural networks, sklearn or scikit-learn is not very strong because neural networks are just another breed of machine learning model. So we have some specialist kinds of libraries that we use. The foremost one initially, we used to have Theano, then we had the TensorFlow, right? There were C++ based libraries, the Theano and the Torch. And then we had, Theano is Python based. Torch was C++. But Torch was ported to Python, and that's what we call PyTorch. And then TensorFlow, which again was created by Google. Now we have a bunch of others. So, for example, we have JAX. JAX is a new framework. So, we're going to look at some of the frameworks that you can use for training and inference with neural networks. So, by the end of this week, you should be able to explain how a neural network is able to do what it does, process data. You should be able to understand forward propagation and backward propagation, and then implement a simple feed-forward neural network in PyTorch. Um, then today we are going to talk about a bunch of things. So we'll start with talking about a perceptron, a neuron, layers, and then forward propagation. And we'll also talk a bit about the backward propagation, and then the intuition around training a neural network. Okay, so let's go. So what's a neural network, right? Um, a neural network is basically an embodiment of a linear model. So we started off this training by looking at linear regression. And then we looked at linear regression with single variable. We looked at linear regression with multiple variable. Then we looked at logistic regression, right? Now, all of those were kind of prepping everyone for understanding how neural networks, work basically. A neural network is made up of entities that we call neurons. And I'm going to go into that shortly. But why do we even need to go beyond just, linear and logistic regression? Why isn't that sufficient for all of our AI needs, for all of our, intelligent, um, modeling, of the data and the events around us? And the reason is simple, right? Um, the main limitation is that in the real world, the data and the relationships between events that you want to model or predict are never linear. They are often nonlinear. Now, they are not just nonlinear, they are nonlinear to a very high degree, to a high, dimensionality, right? And you cannot even say, okay, I want to represent it with a polynomial. The polynomial is not even enough because these are not smooth relationships. A polynomial will give you a smooth curve, right? So effectively, a linear and logistic regression is not enough because these are based on um, a linear decision boundary. Okay. And while they are very good for simple, what we call simple linearly separable problem, they will not work for real world, problems where the data is nonlinear, the relationship between the data is nonlinear, the things you want to predict, they are nonlinear. So the linear models will struggle with those, right? Um, complex patterns, feature interactions, sometimes we don't, in a linear model, it's kind of assumed that um, feature X1 is not affected by feature X2, right? But in the real world, that may not always be the case. You will have a situation where you actually have features that kind of inter they interact, right? They kind of they affect each other. So for example, if you're trying to model rainfall, then you have temperature and humidity as your independent variables that you plug into a linear or logistic model, right? Then you're assuming that the temperature doesn't affect the humidity and that the humidity doesn't affect the temperature. But the question is that assumption actually correct? The answer is no. That assumption is wrong because there is a bit of interaction, right? There is a bit of, it's not a complete correlation that you say, okay, it is, a common mode correlation. So you would say, okay, let's remove one of the um, features because they are basically duplicate features, right? But there is a little bit of interaction, those um, between those features, between those patterns. So a linear model will begin to struggle with that because when those begin to influence each other, you are assuming that there is no correlation between them, but there is. And because there is a correlation, um, then you also have a situation where the models will interact. So your linear model will struggle with it, right? And so that's an interesting case. And then there are other situations as well, which, patterns that are very complex, right? There are patterns that are very complex, and complex patterns um, are definitely going to be very difficult for linear models to represent, right? Then as well, hierarchical representations or hierarchical relationships between data will also be very difficult for you to represent with a linear model. So, having looked at all of that, machine learning would not be useful in the real world if we were just depending on linear logistic regression and all of the other classical machine learning algorithms, which is why machine learning and AI did not kick off for a while because there wasn't any, you know, system or algorithm or approach that was robust enough to represent the real world or the real life until neural networks. Neural networks always had the promise, but the problem with neural networks, it had its own limitations, and we're going to look at some of those limitations and how they overcome, right? But I think one of the biggest limitations with neural networks is they consume a lot of data for you to train. That's the first one. And then secondly, they consume a lot of computational power for you to use them to evaluate anything, right? So while that difficulty was not surmounted or resolved, neural networks were not very useful, right? But we always saw that you could do stuff with neural networks. You would see that one of the ways that neural networks are able to solve these limitations of linear models is by stacking linear models on top of each other. So a single neuron is a linear model. A single layer, which is made up of neurons that are in parallel, becomes a nonlinear, um, you know, um, model. And then you add an activation function. The activation function introduces additional non-linearity. And then you stack layers. When you stack layers, um, those layers introduce additional levels of dimensionality. So neural networks now turn your single linear model into a multidimensional, from a linear model to a plane to a hyperplane. So neural networks solve that the problems of linear models by stacking multiple transformations. And all of those transformations are learnable. In other words, as you are training the model, you are learning parameters, right? And, we'll look at some of the parameters that you learn and the ones that you don't learn in neural networks. So, stacking multiple transformations, learning nonlinear representations, and automatically discovering useful features. So this is another very key part of neural networks. In most other machine learning models or algorithms that you use, you have to do a lot of feature engineering because those models are so simplistic, right? You have to do feature engineering. You have to add additional, maybe second order or third order, aspects of the features, right? You have to create additional features either by combination, by subtraction, difference, multiplication, addition, and so on. So there was feature engineering was a huge deal prior to neural networks coming on its own. But when deep neural networks came into play, feature engineering kind of, I wouldn't say lost relevance because we still do a bit of feature engineering. But in most cases, you don't even really need to do feature engineering because the neural networks themselves begin to identify and discover new features on their own. In other words, essentially built-in feature engineering. Because you are stacked, especially with deep neural networks, you are stacked so many layers. Every layer basically converts the features of the previous layer and generates a new set of features for the next layer. That's essentially what happens when you put up neural networks. So you can set up a deep neural network and just bring in the raw data as it was, of course, transformed into numbers as it should be. But you don't need to do any feature engineering because each layer will engineer, what it basically trains, it learns those features as part of the training process. So there's something I'm going to talk about later on about neural networks being what we call function approximators. So for those of us who did a bit of mathematics, right, you could you could represent any set of data that you plot on a graph. You can find a curve to fit through those, right? If you find a curve to fit through those, you have to identify a mathematical function that represents that curve or that line of best fit, right? So we have in traditional maths, right, or numerical methods, we would have to try look for ways. There are different ways using rank correlation, using line of best fit, using polynomial approach to fit functions into those data points, right? But the interesting thing is that a neural network is actually a function approximator. But it is an interesting kind of function approximator in that you don't need to calculate the coefficients, just like what we were doing when we looked at linear regression. So we go back to the linear and the logistic regression. We were able to find that by training and trying to fit the model into the data, you are adjusting the weights or the parameter. The parameters are the coefficients of a multivariable linear equation that is supposed to match the data points, right? That's the same thing. A neural network becomes a very powerful function approximator because it can fit almost any kind of data, no matter how complex, no matter how they are scattered, the data points are scattered around. It's able to fit it so well. So that's another way you can view neural network. And I'm starting with that, right? Because I may not mention it again, but then maybe later on down the line. So having given that intro, I want to start off by asking, where did this whole idea of neural networks come from? It came from biology. And this is one of the reasons why I love neural networks as a solution or as an algorithm in machine learning, because it's based on the human brain. Yes, it's not exactly the same as the human neuron, right? But if you have gone to study neuroscience, I actually took some time to study a little bit of neuroscience when I was learning about neural networks. So you find that the human brain is made up of billions and billions of cells. Those cells are called neurons, right? They're called neurons. And we are going to see in the next slide how that relationship between each of the cells in the human brain, actually, basically, the entire human nervous system is made up of neurons, right? So the neuron is a cell that has extra electrical activity. So signals are transmitted from one end to the other. And unlike most cells, which are secular, well, according to the drawings and the images we see, but a neuron is not always secular. It basically looks like an organism. It has a head and a long tail, right? And on the head, it has some hairs, right? So that's how the human, brain is. So that's the biological inspiration of this neuron that we use for neural networks. And if you look at it, in the neurons in the human brain and in the human nervous system, basically they receive signals, they process those signals, and then they produce outputs. So this kind of principle was copied by researchers of those days. The whole idea of artificial neurons started a long time ago, way back in the 50s, 1950s, or maybe even earlier, right? They were basically trying to figure out what's the best way for us to simulate human intelligence. So the most logical answer is to look at how the human intelligence actually works. So a mathematical model was, devised and presented to simulate um, the human biological neuron. And that mathematical model also has inputs, and then it has weights, and then it has a weighted sum and activation. And we're going to look at that shortly. So it's a very simplified mathematical model. In fact, one of the reasons why the artificial neuron was so simplified was to make it easy to calculate and evaluate the outputs given a particular input. Because if it was too complex, there wasn't enough computational power in those days for you to even do a complex model. It was not never going to compete against existing models, which we've talked about some of them, including the decision trees, the support vector machines, the linear logistic regression models, and all those models also existed then, right? And there were even others that were not machine learning models, like knowledge, the the AI, knowledge-based reasoning, case-based reasoning, and all of those ones that were based on expert systems that were, fuzzy logic that were based on human beings writing out the rules, right? Rule-based systems. So there was during the period of the heydays of AI research, a lot of people were trying to look for ways just to make their own ideas fly and get funding. So the artificial neuron has a very high simplified mathematical model, which we are going to look at. The interesting thing is that you're not going to get headache because the simplified mathematical model of a neural network or a neuron is a linear regression. In fact, it's a logistic regression. That's what it is. So if you have already mastered logistic regression, good, you will not have a problem. So now, but the one thing that we always want to let people know is that when we say neural network, it is not a simulation of the biological neural network, right? We are not simulating it. In other words, we are not trying to exactly copy it, but kind of borrowing ideas from it. And then borrowing those ideas from it, simplify it into a mathematical model that works. That's basically um, what the artificial neural network is. By the way, mind you, in those days, neural networks, we used to call them, or neurons, we used to call them artificial neurons to kind of differentiate them from the biological neurons. But these days, people don't even differentiate anymore. They just call them neural networks or neurons because it's kind of understood now. Everybody understands what those are. So neural networks are not biological simulations. They are basically engineering tools. Engineering models have been optimized for max high-speed computation. So looking at the biological neurons, what has been maintained compared to the biological neuron is the weighted signal combination. and then the layered processing, right? Because if you look at a neural network, the artificial neural network, the architecture, it has layers, but the brain doesn't work with layers. The brain, the way the neurons in the brain are connected is crazy. It's not easy for you to map, right? So yeah, so the things that we do not look at when we are comparing the biological neurons with the artificial neurons, the chemistry. So first of all, the biological neurons use electrochemical interactions to transmit signals. And this so it's really interesting to go study neuroscience, right? Drugs, when people take drugs and get addicted, what's actually happening is the things that allow your brain or your neurons in your brain to send signals. These are the electrochemical signals, is what we call dopamines. The dopamines are chemicals that have electrical potential. So each type of dopamine has a type of function. Now, what happens when you get addicted to a drug is that you begin to consume those dopamines. So first of all, the human body naturally produces those dopamines in small quantities because they are needed for the brain function. But when you now overwhelm your brain by taking external dopamines, you take them, in large quantity, your brain basically shuts down its own internal production, right? And when it stops its internal production because you are giving it an external supply. But what now happens is when you cut off your own external supply by stopping to consume those drugs or dopamines, right? The brain does not immediately resume its own internal production. The human body doesn't immediately resume. So you lose access. Your brain will not have those chemicals and your brain begins to malfunction. And you start having depression and all kinds of things. That is what we call, um, what do you call it? When you stop withdrawal symptoms, when you stop taking a drug that you're addicted to. Addiction is simply a condition where you have taken drugs that your brain needs to a point that your brain stops producing it. So you now have to be supplying it externally. So that's just an aside in terms of the chemistry of how the human brain works. Again, take time and read some neuroscience. It's very interesting. So when we talk about neural networks, we don't look at the chemistry of it, right? We don't look at timings. Our own neural networks or neurons are highly simplified. We look at signals, what we call step functions, but in the brain, there's what we call spike signals. So a change in a potential is also considered as a signal. But and there are new designs that are trying to more closely mimic the brain. I'm not going to go into all of that detail. So things like chemistry, the timing, and the complexity of the interconnections between the biological neurons in the brain. Those are things that we currently cannot, mimic. So we forget about that. What we have is good enough, right? What we have, the simple mathematical model, which doesn't use electrochemical or it doesn't use chemicals to generate signals. It's basically just ones and zeros, bits and bytes. Is good enough to give us what we are seeing with the large language models. So it's a miracle as far as I'm concerned. So the neural networks succeed not because they mimic the brain perfectly, but because they are mathematically efficient and trainable. The most important thing is trainability, the fact that you can train them. So let's now delve down into the building blocks. What is a neuron? So I'm going to look at a neuron, which is the biological neuron first, right? So a biological neuron, which is the one that's in the human brain, is a basic unit of the human brain. It receives other inputs from other cells. So if you look at this drawing, right, this is the level of complexity. It starts off, the human brain has billions of um, blobs or groups, what we call lobes. And there are so many different medical terms, right, which are basically groups of neurons, right? Or neural networks. A group of neurons that are connected in a logical manner is a neural network. And the brain, you have neural networks. So you have biological neural networks. The neural networks are made up of individual neurons. And this is how the individual neuron looks like, right? This is the cell body. This is the part I call the head. This is the nucleus. So for those who did a bit of biology, right, every cell has a nucleus, right? But these nerve cells are very special. They also have these things that stick out, from the cell cytoplasm or the cell, body. It's called dendrites, right? And then you have this really long one that goes all the way. That's called an axon. So the axon is like a long wire. So think about it this way. The neuron has, um, think of it like maybe a telephone connection. So this is your phone, right? And then this is what is receiving signals, maybe your signal receiver or your camera. And then there's a long wire that goes all the way to the other, to where you want to send the signal to. And at that end, you have the synapses, right, at the end of the axon. So the synapses will connect to the dendrites in the next cell, in the head of the next cell. These three drawings are basically different variants of the same thing. So um, effectively, I drew three different neurons. This is one, this is two, and this is three, just to allow us to see it's the same thing, just drawn differently from three different sources. So if you look at this, right, you will see that, again, you have a nucleus, right? You have a cell body, you have the dendrites sticking out. So this is the head of the nerve cell in the human brain. And then you have the long axon. So you have this other thing you call myelin sheath. The myelin sheath is just a kind of insulation, right, around the axon, just to prevent signal leakage or something like that. I'm not a neuroscientist, so I don't, if I make a mistake, please forgive me. I just did a little study on it a long time ago, many years ago. Um, so the axon sends a signal, and then at the end of the axon, you have the synapses. So typically, the synapses from this neuron would connect into the dendrites of the other neuron. There is a gap between, technically, this synapse is the gap at the end. Here, I can't remember the name of this other end. It's not dendrites, but it connects to this other one, and there's a gap. That gap is what we call a synapse. And the main purpose of the synapse is that, think of it like an air gap for those who are electrical engineers in a transformer, or the distance. There is a certain minimum potential um, energy. Let me just use that terminology that is needed for a signal to cross that gap. So if that potential is not reached, the signal will not cross that gap. So what that means is that the signal will not be propagated or transmitted from this cell to the next. So only signals that the potential is higher than the barrier potential of the synapse will cross over to the next cell. So in essence, the synapse is one of the key elements that determine signal transfer across your neurons, and the synapses can change as you learn. So when you hear that, when people say that as you are learning and your brain is learning, the synapses are learning. In the human brain, the synapse is the parameter, right? The synapse is the equivalent of a parameter, is the thing that changes for you to learn. So this is kind of how the human brain works, right? And it's always good if you're learning neural networks just to start with this. Everybody starts with this. It really makes sense. It relates to us, human beings. So, um, so the basic unit of human brain, the neuron receives other inputs from other cells and fires output to other cells. The synapses link the neurons together and carry the information from one neuron to another. The axon fires when the chemical potential in the neuron exceeds a certain threshold, right? So there is also a threshold that we call, okay, let me rephrase that. There's a threshold in the body of the cell in the axon that you need to reach. That's where the threshold is. The synapse is basically something that attenuates the signal. So um, if the synapse is really wide, less of the signal from one cell, one neuron goes across to the other. But if synapse is very close, more of the signal goes across. So it kind of mimics the width. Then, so when you now take all of these interactions, right, and you put them together, think of a billion of these things, right? This is what results in, you know, memory, intelligence, and all whatnot, in the human brain. So the combination of different neurons via the synapses results in the advanced human brain behavior, right? The average human brain has about 100 billion neurons, 100 billion neurons. So the intelligence is not as a result of a single neuron, but as a result of mass, the massive number of neurons, each of them having a slightly different, you know, connection to the other and so on. Over time, which you also learn. That is what results in intelligence. And this is the same thing that we now simulate with our artificial neural networks. So, what is an artificial neuron? Artificial neuron is basically a mathematical model that simulates the human, neuron in the human brain on the nervous system, right? And in these days, we don't bother to call it artificial neuron anymore. We just call it a neuron. By the way, for some of you who may have had previous, um, you know, um, you have encountered it previously, and you may be hearing interchangeably they use the word neuron and perceptron. Those are not exactly the same things, right? But for most purposes, for most intents and purposes, you can consider them the same. So a perceptron is the simplest form of a neural network unit, right? Um, Essentially, a neuron is a more modern implementation, mathematical model of a perceptron. A perceptron was the first mathematical model of the biological neuron. And I'm going to talk about the difference between them shortly. So it's a basic unit. It has a mathematical model that implements a simplified behavior or a simplified version of the behavior of human and animal brain cells, right? So if we now do the mapping now, remember we're talking logistic and we're talking linear regression with multiple variables. So let's start with there. In the linear regression with multiple variables, you have inputs, which are the multiple variables themselves, x1, x2 to xn. And then we have the parameters that you multiply the coefficients of each variable in the linear equation, right? The weights. So in neural networks, we call them weights, right? And we use symbol W, right? In the previous things we were doing, we used theta, we used M and all kinds of things, right? But it's all the same thing. Basically coefficients that you will multiply. So, and then you have the bias. So the bias is a representation of already the tendency of that neuron to behave in a certain way. And then we have what we call the activation function. We're going to talk about activation functions shortly. But the activation function is kind of simulating the activation potential of the axon, the cell, which means that the signal strength that goes into the neuron needs to get to a certain point, right? Before it gets triggered. Well, that was the original formulation of activation function. But now we have different kinds of activation functions, which we'll talk about. So when you look at all of this, there is a direct mapping. The inputs map to the dendrites, in our brain model, the X1 to XN. The weights map to the synapses because the weights determine how much of the signal actually passes into the neuron, right? And then the bias is already kind of the signal that is already uh, in the neuron without any input coming in. There's already a kind of tendency. The neuron is already having some kind. That's why it's called bias. It already has some kind of bias, right? And then the activation function, like I said, is mimics the neural potential in a biological neuron. And then, of course, the output, which is the axon. So that's the output that goes out. So if you look at this, this is a very generic mathematical representation of a mathematical model. So basically, this summation sign means that each of these is a dendrite, right? Representing an input. And then for the input to go into the dendrite, it passes through the synapse. So the synapse has a weight. And in this case, WK1, right? WK2, WKN. So each of these weights are basically parameters. And um, then they all go into the body and they are added together. The signals are added together. So you can see that because the signals are added together, it is a summation function, right? And then after adding the signals together, you get something that comes out, which is a linear combination of the different inputs across the different weights. And then it passes through this function f of u, which is an activation function that basically represents the activation potential of that cell, of that axon. And that is a mathematical model. So how does it work? Typically, you take each input, multiply by its own weight. Each input has a weight. That weight is a parameter that the neural network or the neuron is learning. That weight remains fixed and unchanged. The weight is what holds the knowledge. It's the parameter, just like when we're doing linear regression and so on, so on. The weight, the knowledge is in the weight. Once you change the weights, you change the knowledge that that neuron holds, right? So the weight is what you train when you are training the neural network. So you take the input is whatever data that you want to analyze or that you want the neural network or the neuron in this case to predict an output. So that data, like we did last time, we convert that data into some form of into a numerical form, right? Irrespective of whatever may have been the original the original form of the data. It could have been a word, it could have been an image, right? It could have been anything, but we convert it into numbers. And that's what we were doing when we did feature engineering. And we talked of all the different ways that you can feature engineer stuff, right? So that is, you know, you take each of those inputs, you multiply by the weight, and then you sum it. When you sum it, you add the bias term, which the bias term is a representation of the existing state of that neuron. And then you apply the activation function, and that is the output from that neuron. So this is called a neuron or a perceptron, okay? So conceptually, perceptron computes a weighted decision based on input features. I prefer the word neuron, right, for a single element. But if you go check the definitions, a neuron is actually used for the biological neuron, while a perceptron is used to mean the mathematical model that kind of mimics the neuron. Okay, so let's look at the mathematical model now. So it's the simplest form of a neural network or a neural network unit is a basic unit with a mathematical model that implements a simplified version of the behavior of the human and animal brain cells. So that's basically what I had before. Now let's look at the mathematical model. So let's say in this case, this neuron has 3 inputs, right? So each input will have a weight. So you are going to have 3 weights as well. So you have 3 inputs, x1, x2, x3, which are the independent variables that form the data that you want to predict. And then you have W1, W2, W3. Those are the weights, which synapses, the parameters. So it's a very simple linear equation. X1 times W1 plus X2 times W2 plus X3 times W3. It's as simple as that. That is how you arrive at, that calculation. So X1 times W1 plus X2 times W2 plus X3 times W3. So basically a signal that arrives from here is actually X1 times W1 because X1 is the actual signal that's coming, but W1 represents the attenuation or boosting of that signal. It's not the entire signal that comes through. That signal is going to get squeezed, either reduced or increased. That's what I mean by attenuation or boosting. That's the essence of the width. That's the essence of the synapse. It's basically to say it's not the whole signal that came in that will get to the cell body. All right, same thing. So W2 will also kind of affect the amount of this signal that comes in. And when I say signal, these numbers are actually actual numbers. They are floating point numbers. So they are not like zeros and ones. They're actual numbers like 0.005, 3. It's numbers. So that means they are continuous. They are in the continuous domain of real numbers. Even though I have to say that the original formulation of perceptron, these were actually binary. They were either 0 or 1. That is why the perceptron originally was not very powerful, because it was so limited in its formulation. And that was because of the weak computational power in those days. So um, that's why I don't like calling this perceptron, but um, it's kind of a technicality there. So when you look at all these three now, you see that what you have is W1X1 plus W2X2 plus W3X3 to whatever number of inputs are there, each input corresponding to a weight, plus the B, which is a bias, which is basically the state of the cell itself or the neuron or the perceptron. So if you look at this, and if you remember when we started, this is what? This is the equation of what? Who can tell me? This is equation of
A straight line.
multivariable. Yes, thank you. Straight line. It's a multivariable linear regression equation. It's a multivariable linear equation, right? This is going to give you a linear combination of this, right? So that is what comes out of here. So what comes out of here is Z, which is the um, linear combination of this. Now, you take this Z and then you pass it through an activation function. That's what this F represents. So this activation function is basically a function where you pass the linear combination through it, and then that what comes out. So actually Z is not this. Sorry, Z is the summation of Wixi, which we can also represent, in vector format, in the vectorized format with W transpose X plus B, right? Where W is a weight or the parameters. X are the inputs, the same X we've been using. The variables, um, that come in, independent or dependent. And then the B, of course, is the bias in the cell. That is what is the output of this. So you can now see that finally the final output is the Y hat, right? Is a activation function F of Z. Now I want to ask, I don't know who can remember, you can type in the chat, which formulation that we have seen in the past had this form where you had a linear combination and then you pass it through an activation, through a function. Let me not call it an activation function, but that's what it was. We passed it through a function. Who can remember? What was it? Who can remember? Good. Sigmoid. Somebody said sigmoid. Yes. But that is in what? Logistic regression. It's logistic regression. So with logistic regression, we're effectively doing the same thing that a neural network does. And for me, this is a slam down. When I was studying neural networks, I didn't know that, because when I studied neural networks, I didn't study logistic regression. I started off studying neural networks first before any other thing, right? And then later on, I studied this other one, and then I'd say, what? It's the same thing, right? So the only difference is that for logistic regression, it has to always be what? A sigmoid function, right? That activation function has to always be a sigmoid. But for a neural network, you can use any number of activation functions, depending on what you want to do at that material point in time. So let's look at what is the difference between a neuron and a perceptron. So a perceptron is an early model, right, of a single layer neural network. You can see that they use a terminology single layer. It's not even a single neuron. So a perceptron actually can also refer to the entire layer, right? But when we are talking about neurons, it's not the entire layer. It is just a single neuron. So, um, but the main difference is that for neurons, you have a nonlinear activation function. I think that's the most important thing that I would like us to kind of pay attention to here, right? This drawing here is a drawing of a perceptron, by the way. This is a perceptron, right? Now, why is it a perceptron? The only reason why this is a perceptron is because of the activation function here. We use what we call a step function or a binary true-false function, right? So a perceptron was designed to only work with ones and zeros. So what that means effectively is that if the summation of this linear combination of the inputs across the weights, if it is above a certain threshold, then the output here will be 1, right? But if it is below a certain threshold, then the output will be what? 0. That's why you have this piecewise linear equation that says if O, which is the linear combination of the individual inputs across the weights, that is the summation Wixi, right? If this sum is greater than or equal to 0, then the output will be 1. But if the sum is less than 0, then the output will be 0, right? So this was basically what a perceptron was. And in this formulation, where the perceptron could only have a value of either 0 or 1, it had a lot of limitations. If I want the limitations, well, that's not why I had that limitation, but one of the limitations, for those of you who may have looked at it, you'll be wondering, there used to be this question of um, the XOR problem, that you cannot solve the XOR problem in a neural network. I got, the thing kind of made me crazy at some point, but um, the real reason for that issue is because a single neuron is a linear model. It has a line as its decision boundary, which we are going to talk about soon. Because it has a line as its decision boundary, it cannot solve the exclusive OR problem because the exclusive OR problem cannot be solved by a single line as a decision boundary. We talked about decision boundary when we were talking about support vector machines, if you can remember. We were talking about where you put the line to separate two groups or clusters. We'll see that shortly. So, but anyway, neurons use nonlinear activation function. In other words, a neuron can use any different type of activation function, but a perceptron only uses a threshold activation function. And that's what I just showed here, right? What I just showed here is just a threshold, right? Um, because why is it a threshold? The threshold in this case is 0. If it is above 0, then it is true. If it is below 0, it is false. So that is how that's the first difference, right? Then the second difference is that the output of a neuron is not necessarily a binary number. In other words, it can be a floating point number. It could be 2.5. It could be greater than 1. It could be less than 1. It could be a decimal. It could be anything, right? It could be negative or positive. But for a perceptron, the output of a perceptron must always be a binary number. In other words, it must always be either 0 or 1. And again, that was one of the limitations of the perceptron in those days, right? So that's something, again, to pay attention to. So that's 2. Then the third one is a perceptron is actually a standalone model trained with a specific algorithm. In those days, perceptrons, there was nothing like, layers or stacking of layers of neural networks or backpropagation. That didn't exist then as an algorithm, that the knowledge of AI didn't get to that point yet. So the only way you could solve a perceptron or use a perceptron is it could only be a single layer, right? Where you can then calculate the parameters and then do that. So like I said, a single neuron or a single layer is incapable of solving complex problems. So that was a limitation. But the neuron is designed, like by definition, a neuron allows you to um, composite, combine multiple neurons to have layers, stack multiple layers to have deeper neural networks. And all of this is possible for you to still train those deep neural network models, what we call deep learning, by applying the back propagation algorithm, which we are going to look at shortly. So those are the main differences, right? So because neurons can be combined in so many different ways, and I remember I just said that a neuron is actually approximate, it's a function approximate to a single neuron. So when you combine multiple neurons, you can approximate more complex functions. So A perceptron has historically been shown to be unable to solve the XOR problem. And that's simply because it's a single layer. That's one. Then the second additional problem is that it is only binary. It can only have zeros or ones, right? So the neuron is the smallest computational unit of a neural network, right? It's an abstraction for a relatively simple function. Example, sigmoid. So the activation function, that's it. That function is composed on top of the linear combination of the inputs across the weights, right? And that is basically what a neuron is. So whenever you hear neuron, in the context of the artificial neural network, it's a mathematical model. It's basically a linear regression or a linear or a logistic regression with multiple variables. That is what it is. But now, what makes neurons so powerful is the fact that I can now combine a lot of them, right? But before we go into that, let's talk about why a single neuron is so difficult to solve. It cannot do a lot, but multiple neurons can do a lot. So if you look at geometry interpretation, let's look at this. So if you look at this, you will see that I did something like this when we were doing the support vector machines. So you have two clusters here, right? And then what you want to do is you want to draw a decision boundary. The correct solution to this problem, not what you have on this drawing. The correct solution to this problem will be a boundary like this, because this is what separates the reds and the blues across this boundary. Now, if you were to use, if you go with this line that has been drawn here, you see that it's a poor decision boundary. But this is a simple, what we call linearly separable set of data. You can draw a single line here and you can say, okay, anything that's to the right of this line or above this line is red, and anything below this line is blue. Simple, right? And this linear relationship is defined by this W1 X1 plus W2 X2 plus B, the bias, which is equal to 0. So again, remember, in the case of a perceptron, this will be 0 if this total sum, right, is what? Is below, its actual value is below 0. Its output will be 0. But if the actual value is equal to 0, above 0, then the value will be 1. We just saw it. So, but because a perceptron, you cannot combine multiple perceptrons, right? So a perceptron cannot solve the problem that is not linearly separable, right? Um, but for a neuron, you can then you can have higher dimensions, and then you can have multiple combinations stacked, and you can now have the decision boundary becoming what we call a hyperplane, which I talked about. If you go back and check the class on support vector machines, I spoke a lot about hyperplanes and the fact that when you have a projection of in it from a 2D space into a 3D or multidimensional space, then you can take a line in the 2D space, which becomes a plane in a 3D space, and you cut the hyperplane, and you will get a decision boundary that may not be a straight line. It may be a circle or some other shape, right? So just a reminder to go back and check that class. So this is just telling us that, oh, okay, this is why, because you want to classify, you want to do whether it's classification or regression problem, you want to draw a boundary that says um, you want the neural network to learn, let me not say draw, because that's not the right thing, but you want the neural network to learn a boundary. And this boundary can be any of these, right? Because of the fact that they are, there's a lot of space in between them. The boundary is flexible. It can be any number of things. But there are some situations where this boundary is very tight. So it has to be very accurate. Okay. So classification rule in a perceptron. Remember, we're talking about perceptrons and perceptron as a decision boundary. The classification rule in a perceptron is that on this side of the hyperplane, like this side, right? Then you classify it as class 1. That is, the red ones are class 1, right? While on this side of the hyperplane, these blue ones, we classify it as what? Class 0. So that's just simply how, you know, perceptrons work. Okay. Um, so, but let's look at now a more difficult problem, the exclusive OR problem. This is a graphical representation of exclusive OR problem. Exclusive OR problem is a problem that says that when the values are the same, then it is true. But when the values are different, then it is false, right? And when you take it and plot it, you get something like this. And the reason why you have, so class 1 is saying true, right? Sorry, class 1 is saying false when the values are not the same. But class 0 is saying what? True when the values are the same. If you look at this, so let me again draw a line around the decision boundaries. You will see that here, right? If you look at this, this is 1. Let's just look at the center. Forget about there's some noise in the data. I deliberately introduced some noise in the data so that if you wanted to use a perceptron to classify this, right, and do prediction, we will not have a single point, right? But if you look at this, this is 1.0 and this is what? Minus 1.0. So they are different. That's why it is false. This one too, this is the x1 is minus 1.0 and the y is 1.0 and the x2 rather is 1.0. So the prediction is false. They are different. But these ones are the same because these ones are basically the same value. So these ones would be classification that these two are the same value. And again, if you look at it here, this is 1.0, right? The x1, this axis is x1 and this axis is x2. So the x1 is 1.0 and the x is 1.0, so they are the same. Okay? So that means they are true. This one, the same thing. This one, the x1 is minus 1 and the x2 rather is minus 1 as well, so they're the same. So this is exclusive OR. Exclusive OR is saying when the two values are the same, it is true. But when the two values are different, it is false. So in this case, we gave class 0. True is class 0. False is class 1. This space here, this problem is not linearly separable. What does that mean? You cannot draw a single straight line that will correctly classify these 4 points. You will always be wrong half of the time. You will always be wrong half of the time. This is why perceptrons could not solve the exclusive OR problem. Because let's say I train my perceptron to draw this as a decision boundary, right? Let me draw that properly with a different color. If I train my perceptron, draw the decision boundary here, right? Now, this case, let's even say that up here means true. True is class 0, while false is class 1. You see that we are wrong half of the time because we are saying that everything up here should be class 0, and class 0 is blue. So what that means is that this half of this classification is correct. The other half is wrong, right? And the half that is correct, this is the half that is correct because this one is saying it should be class 0, which is blue, and it is blue. But this half is wrong because we are saying it should be blue, but it is not blue, it is orange. In the same way, this other lower half is also wrong because in this case, we are saying that class 1, which is orange, but this is blue. Down here should be orange, but it is blue. So you are not able to get a correct answer. This one is correct, by the way, right? So only these two, the one up here and down here, are correct, while these two are wrong based on this decision boundary that was drawn here. So you can do the same mental thought experiment and draw more decision boundaries and say, okay, did I actually classify it correctly? Let's draw another line, right, to represent another decision boundary. Since it's linear, I'm going to just do straight lines, okay? So I'm going to just draw another decision boundary and say, okay, instead of drawing, the first one was like this, right? So instead of drawing that, let me draw this. And then if I draw this, then I'll say everything to the right is true and everything to the left is false. So everything to the right is true and everything to the left is false. But again, remember, true is what? Blue, and false is orange. But since we say everything to the right is true, it's only this one that is correct, that I predicted correctly. Only this one. And then only this one I predicted correctly. This other two down here predicted wrong. Because I'm saying anything to the right is true, but these orange ones are not true. These orange ones are false. So I did not predict correctly, right? So this is mispredicted. This is mispredicted. So again, half of your prediction. So you can now say, okay, let's try something. Let's even try something more adventurous, right? And say, okay, let's draw a line like this. So someone can try and be smart and say, okay, let me draw this kind of line. Yeah, okay, nice, nice, good. Let's analyze this. Okay, so if you draw this line, then you look at it and say, okay, anything above is true and anything below is false, right? Anything above is true and anything above is false. But that would be really bad. So let's say anything above is false and anything below is true. You have trained your model to eventually come up with that. Anything below is true. So this would be okay for just three of the points, while one will still be wrong, right? This one will be correct because you're saying anything below is true and this one is true. True is a blue color. And then anything above is false. So this one will also be correct because this is false, right? And this one will also be correct. It is false. But this blue is not false. It's true and it's above the line. So again, we have misclassified this one. So you cannot get 100%, this thing with a linear. That's basically why that's why we're saying only one neuron is not enough. So this is why we now have entire networks. You cannot solve the exclusive OR problem with a single straight line. You cannot do that because the exclusive OR problem is not linearly separable. In other words, you don't have in a situation where you can draw a single line and divide them into two sides. If you wanted to even try something, you could then do something like this. This is more or less like a proper solution, which I don't even know. Maybe a proper solution would be something like this. Yeah, I need to actually draw a proper solution will be this kind of decision boundary, right? Where you now say that everything inside here, everything inside, right, is true, and everything outside is false. But is this a linear? Is this a straight line? This is not a straight line. You can solve this with a circle, right? But you can't solve it with a straight line. So, but because a neuron is the model of a neuron is a straight line, you cannot use a single neuron. But the interesting thing is that when you combine multiple neurons, it becomes not just a multivariable model, it also becomes a non-linear model, especially when you add the activation function. It becomes non-linear. And because it becomes non-linear, the more the neurons you add, the more non-linear it is capable of being. The more it's capable of wangling itself around weird decision boundaries like this. Because in real life, data the relationship between data is not straight line like this. You have things mixing in and out. So a neural network needs to be able to figure out that as you're training it and it is adjusting and you're trying to minimize the loss. Remember, you're training it by minimizing the loss. It will adjust itself and find that decision boundary. So what is the solution? You have to combine multiple perceptrons and add what we call hidden layer. So that's where the concept of hidden layer came about. And then you have multi-layer neural network. So in a perceptron, it was solved by adding a hidden layer. We're going to talk about that shortly. Okay, now let's talk a little bit about activation functions. So I'm kind of taking all of the different bits and pieces and try to pull everything together. An activation function If you don't have an activation function, what you are going to do essentially, or what will you end up doing, is that you are stacking a bunch of neurons, right? So let's say you stack a bunch of neurons like this, right? There are so many images of it. If you stack a bunch of neurons, I'm not going to do the mathematics of it here, but I can guarantee you that by the time you combine those neurons and do a mathematical equation on it, the output from a stack of neurons is still another linear equation. It is still another linear equation. And it's very simple to think about it. So think about it this way. Let's assume there's no activation function, right? You have a input coming into this neuron. This neuron represents x1 w1 plus x2 w2 plus b, right? Let me type it in so we can follow with it. So here is x1 w1 plus x2 w2 plus b. So let's just go with a simple one that has just three parts to it. Okay. Now this is one neuron. I can still take this and you have a second one here, right? Now let's call this x3 w3. This is a different neuron, right? But the x's will be different and the weights will be different. X3 w3 plus x4 w4 plus b. Let's just call this b2 so that I can differentiate between the b's. I lost this one, so but let's just, and then this one too, you have x5 w5 plus x6 w6, right? Plus b3. If you do an evaluation of these three combined without an activation, the non-linear activation function. That's why the activation function has to be non-linear. It cannot just pass through the inputs to the output like that. If it does that, it fails in its function. But by doing a little bit of modification of the linear combination of the inputs and the weights, it introduces a non-linearity. But without that non-linearity, what you would have gotten from here is basically going to be a combination of this uh, this 1, 2, 3. You are basically going to end up with x1 w1 plus x2 w2 plus x3 w3 plus x4 like that, all the way to plus b1 b plus b2 plus b3. This is what you get here. So what you just end up getting is another linear equation. Basically, it is the same thing as if you had a single neuron that had more inputs. Basically, it's the same thing as if you had a single neuron with 1, 2, 3, 4, 5, 6 inputs, and then this combined bias. So without the activation function, you basically, if you combine neurons, you just end up as if you had a single neuron. So you would not be able to achieve that non-linearity or the capability of a neural network or a layer in a neural network to um, be non-linear. It needs to be non-linear for it to be able to solve complex problems because complex problems are non-linear. So that is why we have activation functions. I just needed to explain that in case, okay, why? And they are that's what I'm saying is basically what we have here. Multiple linear layers will collapse into a single linear transformation if you do not have activation functions. But when you have activation functions, then the activation function itself introduces a non-linearity, and that non-linearity allows you, when you combine multiple neurons, you now have a non-linear function approximator. And with that, it is able to learn and predict complex patterns, right? And approximate complex and arbitrary functions, any kind of function. The fact that if you think about it, that a combination of neural networks is able to play a game of chess and beat human beings, I don't even know what level of non-linearity is involved in that, right? So the main idea is that the activation functions allow you to determine what the network can represent, right? So every hidden layer, which is the second thing, for you to improve the multidimensionality of your neurons to be able to solve more complex problems, you need to add what we call a hidden layer, which we'll talk about shortly. But in that hidden layer, there must be activation functions. And there are four that are mentioned here. There are far more than that. Right now, I don't know, there are probably up to 20 activation functions, all different variants of each other, all with different, advantages and disadvantages and so on. At a later time, we can go into that. In fact, that's a whole area of study for some people. So we have four that are here. We have the than. The than is the hyperbolic tan. You will see that all of these are basically mathematical equations. Then we have a ReLU. ReLU means rectified linear unit. So basically, what is rectified linear unit? For those who are electrical or electronics engineers, you know what a rectifier is. A rectifier is something that allows signal in one direction, but it doesn't allow in the other direction. That's why it is called a ReLU. Because essentially what is happening here is that the normal linear signal is allowed on the positive side in one direction, but on the negative side in the opposite direction, it is not allowed, it is zero. That is that's why it's called rectified linear unit. It's rectified. It's basically a linear unit that is rectified. It's a straight line, but the negative part of the straight line is chopped off and it's always at zero, right? This is a linear unit. So you can see a linear unit, it will, if the negative part will still keep going backwards this way, right? It's not rectified or chopped off like in a ReLU. The sigmoid, we talked about sigmoid already when we're doing logistic. It's the same sigmoid, so I'm not going to go through that. So these are four examples of the activation functions, and there are a bunch of others as well. So what is an activation function? Well, I've kind of almost already explained it all, right? But in biologically inspired neural networks, the activation function is usually an abstraction representing the rate of action potential firing in the cell. Basically, the axon, that part, right? So it's a binary function, meaning that either the neuron is firing or not, right? And neurons, these biological neurons we're talking about, it cannot fire faster than a certain rate, right? But in a mathematical model, we now kind of abstract it to mean the same thing, right? But you allow the neuron to activate only when the particular um, output based on the function, right? When when the linearly combined input. So again, the linearly combined input is the x1 W1 plus x2 W2 and so on. That's the linearly combined input. It gets to a certain level. When its value reaches a certain level, that's a threshold. That is actually a perceptron definition, right? But when you talk of perceptron uses threshold. The piecewise, if it is above zero, it is one. If below zero, it is zero, right? But others like ReLU will not cut it out and say it can only be one or zero. It will allow the full value to come through. And ReLU is normally used for regression. You don't, if you want to use, if you want to train a model for regression, you typically use ReLU because if not, it will be really difficult. But if it is classification or binary, you can then use a sigmoid or than, right? Which is a hyperbolic than. So that's what an activation function is. It introduces nonlinear behavior, which is needed for the neural network to be able to approximate complex relationships in data. And I don't need to, why are they called activation functions? Because the it's only when the threshold is exceeded that the signal is passed to the next neuron. In that case, the neuron can be considered as being activated. If it is not, if that's combined input signal is not up to the threshold, then the neuron is not activated, it's deactivated. All right. Okay. So the main value of this activation function is that you don't just get any random signal into the neuron to activate it. It has to be a meaningful value. Okay. So there are a bunch of different activation functions. We'll talk more about them. But we have a sigmoid we've talked about already. The range is always between 0 and 1. It's 1 over 1 plus e raised to power minus x, right? Where x is the linearly combined input. It's popular historically, and you can interpret it as probability. That's why we use it for logistic regression. In logistic regression, we are trying to predict probability of something happening. The tan is just like a sigmoid almost, but it's a bit sharper in the middle. It's a bit steeper rather in the middle, right? But the tan has -1 and 1, unlike the sigmoid that has 0 and 1. 0 at the lower end and 1 at the upper end. The tan has a -1 at the lower end, right? And the 1 at the upper end. Then, and it's centered around 0. Then the ReLU I already explained is a rectified linear unit. It's basically a linear function, but the negative part of the linear function always gives you an output of 0. So it's not piecewise, right? It's almost like a threshold where the threshold is 0, right? But the difference is that a threshold would be if it's above 0, is always 1, no matter the actual value of the combined input, right? It's always 1. And then if it is below 0, it's always 0. But the ReLU is kind of a linear where if it is above 0, its value is the same as whatever the input is. But if it is below 0, then it's always 0, right? That's a rectified linear unit. That's a ReLU. And the ReLU is the fastest of all of this because the ReLU is the only activation function that doesn't require any mathematics. It is basically an all function. In fact, you can just use an if statement and say if x is greater than 0, then x equals to 0. Sorry, if x is less than 0, then x equals to 0. And that's it. You don't do any maths. And you see why this matters later on, because when we start doing a lot of neurons, right, these calculations begin to add up and slow down the speed of training of your model or speed of inference. So that's why it is very common, because it is very fast. And hidden layers, you don't want to lose the actual value of your combined input. So you use a ReLU to still maintain the actual values. Otherwise, everything will be zeros and ones, right? It's fast and efficient. Then we have a leaky ReLU. A leaky ReLU is a ReLU, but on this negative side, instead of 0, you kind of allow a little piece of the signal to pass through. So you multiply the negative side by a very small value so that its value, you can see the graph here, you see that it is not really a straight line that is at 0 like the ReLU, but it's kind of slopes a bit this way. So it's actually increasing in negative direction, but at a very low rate. In other words, it's kind of attenuated in the negative direction, but in the positive direction, it gets the full signal. The LU is also another version, right? Which, just like the leaky ReLU, you allow a little piece of the signal on the negative side, but on the positive side, you allow the full signal. The only difference that with the LU, it is programmable, it's dynamic. I can't remember what the E means, but I can remember. But you can change the threshold point. That's the main thing with the LU, right? You can change the threshold point. So if x is greater than or equal to 0, it uses x. But if not, use a certain alpha to kind of attenuate the signal, right? The alpha is attenuation, just like what you have with leaky ReLU. But you use an exponential function instead of just directly having an x. We will look at some of this in due course. So so this is kind of summary of the mathematical equations or formula that we use for the different kinds of activation functions. So you can just take a quick look at this. In most cases, you will not do the maths yourself because all of these libraries can handle all of that. And then let's talk about activation function and gradients. So remember, when we're training models during the linear regression, during the logistic regression, all of that, one of the main, how do you train your model? You calculate the gradient, and then you calculate how much each parameter contributes to that gradient. And then you back propagate. Like, well, we are not doing back propagate actually, because those are not multiple layers, a single layer, right? We just take that component of the gradients that is impacted by that parameter, and we use it to modify that parameter, right, in the negative direction. That's gradient descent, basically. And we use a factor to reduce the impact of the gradient. That factor is what we call the learning rate, right? So this same principle applies to a neural network. When you want to train a neural network, you will calculate the gradient of the entire neuron. You do it per neuron per neuron. You calculate the gradient of the entire neuron. And when you calculate the gradient of the entire neuron, right, you will now, first of all, because you are doing back propagation, the principle of back propagation is that you must pass the signal backwards through every single function. When you are passing it forwards, you are doing the calculation. That's what we call inference or forward propagation. When you do the backward, you have to pass it backwards, and I'm going to show that shortly. So you would have to calculate the gradient of the activation function, just like we're calculating the gradient, of the cost function, which is the total loss, right? Or the cost function, the total loss. Then we now will calculate the gradient of it across the activation function for neural networks, right? We didn't do that for logistics because we use a categorical cross entropy, right? We use a categorical cross entropy, um, which basically, when you look at the gradient of the sigmoid function, it is 1. If you go look at the gradient of sigmoid function, it is 1. So we didn't bother about thinking about it, but you should really pass it through the gradient of the activation function. So one of the things that you will see is that when you take the error and the gradient of that error or the loss, and you pass it through, sigmoid and tan gradients can shrink, can become really small, right? So that as the network is getting deeper, a deep neural network is basically a neural network that has many, many layers. You will find a situation where the gradient becomes so small it does not affect. And why is that so? If we look at uh the curve for a sigma, you see that up here, this is for large values. You will see that the change in x is the change in y is very small. No matter how big the x is, the change in y is very small. That's why the gradient is tiny. And because the gradient is tiny, the impact is what we call the vanishing gradient problem. We'll talk more about it. I'm not going to dwell on it now because basically this will be overloading too much. But um, the main thing is that your activation functions, there are some that are good and there are some that are bad. Each of them have their pros and cons. So when you are choosing activation function, you need to understand what the pros and cons are. I'm not going to go into the details of things like the vanishing gradient problem, which is what happens for some activation functions because they are basically flat. And that's a tan and the sigmoid. They are basically flat um, at certain values, right? So the gradient is very low. Okay. So learning slows in deep networks. So that's the problem with this. ReLU, on the other hand, has strong gradient because the ReLU does not flatten out. ReLU continues to increase. As the signal increases, the output continues to increase. So it converges faster and it's simpler to compute. Like I said, you just use an if statement. Okay. But the problem with ReLU is there's a non-linearity. It's a piecewise combination of two functions, the zero line and the X line, right? Or the Z line, rather. So the zero line and the Z line. So there's a point where the gradient is not continuous. That is another problem, which we'll talk about later on. So that the other drawback is what we call dead neurons. If the inputs continue to stay negative, that means the output will always be 0. So the neurons, all the neurons will always be having 0 values. So for ReLU problems, you use a leaky ReLU. So these are just guidelines on choosing right activation functions. Again, I'll come back to this. I'm kind of rushing through a lot, seriously. So, so don't worry, your brain will be hard to capture everything, but you can always come back and look at the videos, and we'll continue to expatiate and learn more and more stuff. So, so some of the other practical guidelines when you come to activation functions is for hidden layer, use ReLU so that you maintain the linearity, not linearity, you maintain um kind of, should I say, fidelity of the values, right? And then if you have dead neurons, you use leaky ReLU. For output layer, you always use sigmoid if you want to do a binary classification. Remember that sigmoid will always give you 0 or 1. We use it for logistic. And remember, logistic was a binary classification, which was a binary cross entropy. Actually, I should have said binary cross entropy, not categorical cross entropy, but they are basically almost the same thing. It depends on the number of categories. So for for a binary classification of true and false, you will use sigmoid, just like what we did with the logistic regression problem. But for a multi-class classification, you use softmax. We'll talk about that later. And then if you're doing a regression problem where you want to kind of predict an actual value, not a probability or not a classification, you don't apply any activation. On the output layer, we are talking about output layer now, right? Not hidden layers. So that's it. So with all of this, right, we now come to arrive at this slide, which tells us the mathematical model for a neuron, a single neuron. You have each input, which represents a dendrite. If you compare with the human biological neuron, where you have the dendrites, nucleus, cell, axon. You have the axon terminals, branches of axon terminals. The branches of the axon terminals will connect to the dendrites of the next cell through the synapses. So you have the axon from a previous neuron that sends an input into this neuron. It will pass through the synapse, right, which is represented by the weight of this particular input and the dendrite. It goes into the cell body. And you have other inputs from other neurons that are coming in, right? And then all of these inputs are combined linearly. W0x0 plus W1x1 plus W2x2 all the way to all the x's and w's. That is this summation that you have here. Summation of I to n wixi plus the b, which is the bias, which is a kind of property of this particular neuron, right, which is trainable. And then you pass that through this f, which is the activation function that introduces the non-linearity. And this will give you this entire thing in a very simple mathematical function. Summation wixi plus b, passing it through the function. This function can be sigmoid, can be dan, it can be ReLU, can be ELU, it can be leaky ReLU, and a whole bunch of other ones. Okay, so I will pause here. I don't know if there are questions. If you want to ask, you can ask. If you want to type, you can type. This is the total dissection of neural networks, the neuron, the mathematical model, so that you understand that it is basically a combination of linear models, which we have studied before. This slide is the same thing. It is so important that I had to put it two different versions on two different slides. Input layer, you have x1, x2, xn, the values are coming in. The weights, which represent the synapses are coming. The bias, which represents a what's the word now? Well, the bias of that neuron. You combine it linearly to form the Z. Z equals summation from I to N of WI times XI plus B. That is the linear combination. This linear combination is then passed through the activation function to give you your Y hat, which is the value that comes out from the single neuron. Any questions? because we are now going to move fast without um, breaking, too much sweat. I don't have that much time. So now, remember we just said something. We said a single neuron is not enough. A single neuron can only predict a linear relationship between all its inputs. Okay? It can only predict a linear relationship. If it is more complex, you will need to combine neurons. So in our machine learning neural network convention, how we combine neurons is what we call a layer. A layer is basically um, a combination of neurons in parallel. So each neuron learns a different thing. Think of it like a random forest. Remember, when we're talking random forest, we said a random forest is made up of a decision tree, multiple decision trees that are trained differently. They have different, you know, um, we, different parameters, right? So that's the same thing. Yes. No. The first question, what we are basically training, yes, are the weights and biases. That's what we are altering. But for every individual neuron, each neuron has its own different weight. No two neurons will have the same weight, and no two neurons will have the same adjustment to their weights. Their adjustment will be different. So the whole essence of it is that the neurons, each neuron has its own different weight. So they can never be the same, right? Because if they were the same, it's the same thing as having one single neuron. So they all have to have different weights, right? So when you hear a large language model, they say it has 100 billion parameters. What that means is that it has 100 billion neurons, right? Because each neuron, the output from the one neuron becomes the input to another neuron. If a particular neuron has 10 inputs, that means before it, there are 10 neurons that are sending outputs to it. That's what a layer is. So let's talk about layers, right? Like we said, a single perceptron will compute only a single linear decision boundary. In other words, it can only draw a single line to separate, or classify two groups. If, like the XOR problem, it cannot be solved with a single line, then a single neuron is not enough. So what we now do is we use layers to combine multiple neurons or multiple perceptrons, right? So a layer is a collection of neurons operating in parallel, right? So if you look at, we already have a drawing of this, which I put up here. This is a layer. It has three neurons in it, and these three neurons are going to get three inputs that come in parallel. So, well, let's assume each of them have a single input coming in, right? But it's also entirely possible that they can have multiple inputs. So this one can also come, and this one can also come, this one can also go here, and this one can also go here. And in most cases, this is what happens, right? Each input goes to each neuron. So you can see here, there are actually 9 inputs altogether, 9 weights. This neuron has 3 weights corresponding to this. Let me do this, right? So let's say we had an actual input, right? So we have this as an actual input, 3 different parameters, right? 3 different variables rather. Okay, so this particular one has 3 weights, right? This first weight will connect this input, this second weight will connect this input, and this third weight will connect this input. Similarly, the second neuron will also connect these 3 inputs through 3 different weights, right? It will get from here, right? It will get from here, and it will also get from here. This other neuron will also get 3. It will get from here, right? It will get from here, it will get from here. So that's a total of 9. 3 times 3, 9. So the total number of weights in what we call a fully connected, layer is always the number of inputs times the number of neurons. Okay, because each neuron has to be connected to all the inputs. It's like a matrix. And we will look at that when we get to a bit of like manual representation, where you will find that these neurons are actually matrices, and you calculate them and solve them with matrices. So a layer is basically a combination of these, it's a combination of these neurons. That's what makes up a layer. So this is a layer. Each of the neurons in this layer are operating independently. This neuron does not need to wait for this neuron. It can calculate its own and send it to the next neuron or the output. This one doesn't need to wait for this one. It can calculate its own and send. Same thing. This one doesn't need to wait. It can calculate its own and send. So neurons in a layer are independent of each other and they operate in parallel. That means the mathematics that you need to do of calculating the output from each neuron can be done in parallel. There's no interdependency between them. But there's a dependency of this neuron has dependency on any neuron that is sending signal to it. It has to wait for that signal to come before it does its own calculation. So each neuron has its own weight and bias, and all neurons receive the same input vector, which is exactly what we're saying. The input vector is basically the signals that are coming in, and the signals are the same. So the different neurons will collect the same inputs, but how each neuron reacts to its input is determined by the weight. So in this case, you can have a single input also. It's also entirely possible that I can only send one input. I could decide, okay, I am only sending one input into these neurons. So this one will have one, this one will have one, and this one will have one, right? So you have just a single input. But if I have another input coming here, this one can have one, right? And this one will also have one, and this one will also have one. But it's also entirely possible. This is what we call fully connected, right? But there's also situations where you could say, okay, let us not, each one will have its own dedicated inputs, right? Those ones are, um, they're not fully connected layers. So we'll talk about all of that later. But the most important thing is that the input that comes into the neuron are the same. So we have three types of layers. We have the input layer, which is what receives the raw information, the raw data, right? It receives the raw data. Then hidden layers are the ones that you will have and learn the intermediate representations. So remember what I said. Each layer generates its own outputs, but those outputs become input to the next layer. So if you were considering looking at each layer of a neural network as a linear regression, that takes input and output, then the next layer, the hidden layer, is actually getting new features because getting new inputs, it's getting new independent variables, it's getting new features from the previous layer. So what actually happens is that the hidden layers are able to learn new features or what we call the intermediate representations of whatever you're training it to predict. This is very important. And that's why neural networks are so powerful because essentially a stack of neural networks are basically each layer is fine tuning and creating a new set of features that are more useful. It's basically saying each layer is doing feature engineering based on the input from the previous layer and is sending that engineered new set of engineered features into the next layer. That next layer will now take that one, engineer it further, and send it to the next. So by the time the whole stack of neural networks is done, you have a situation where each layer engineers it to a point where you have the final correct output that should come from it. So you have input layers, you have hidden layers. The hidden layers learn the intermediate representations, basically feature engineering. And then the output layer is what you now condition to give you the final prediction. So here we basically have just a single layer here. We have the single layer, which can also be an input layer, right? And then we have an output, which is going to take a combination from the three inputs and calculate the weighted combination through the weights. And then this output can also be conditioned using a sigmoid function if it is a probabilistic prediction, or using a softmax if it is a multi-category probabilistic prediction, or just a straight linear if it is a regression problem, or for any other kind of thing. Okay. Um, all right. So yeah, let me clear this I'm having a difficulty with my. All right. So we now move to layers, right? So the next logical thing, to talk about is, oh, um, we are now talking about layers. So from single neurons to layers. So we have three types of layers. We have the input layer. The input layer just takes the input, the raw data that after you have processed it and you've converted everything to numbers like we did in the last task. Those numbers will get put into the input layer. For the input layer, every neuron is for each feature. So if you have 10 features, x1 to x9 or x0 to x9, x1 to x10, right? You have 10 input neurons in that layer. And then the input layer does not have any trainable parameter. It doesn't have any weight. You're not trying to train it, right? It's just to collect the input. It doesn't have any activation function because it's also not supposed to do anything basically. It's just to collect input. It receives the raw feature value. So this is an input layer. And then when it receives that raw feature, it will then just pass that raw feature exactly as it is to the next layer. Then so examples of how you would set up an input layer is if it's tabular data, you could say 1 neuron per column. If it is images, like if you want to do image recognition, which we will do, very soon, you have 1 neuron per pixel, right? Or 1 neuron per channel, right? Because sometimes if it is a monochrome image, then that will work 1 neuron per pixel. But if it is a colored image, each pixel actually has 4 colors, right? RGB and the alpha. So the RGBA, alpha is the transparency. The RGBA becomes a single vector, which we call a channel. And then if it is text embedding, we could say, okay, 1 neuron per embedding dimension. So, all right, that's then the next layer is the hidden layer. The hidden layer is where all the magic happens, right? Because the hidden layers are those layers that will bring the additional non-linearity, bring the additional multi-dimensionality, convert the single plane, single decision boundary, the single linear decision boundary into a plane, into a hyperplane, which in that domain of hyperplane, it can then do any kind of complex, function approximation, or it can, basically be a decision boundary around any kind of shape. It is a hidden layer or hidden layers that give neural networks their power, right? So hidden layers transform the input space. So that's the first thing, right? And part of how they transform the input space is like what I said. They basically are feature engineering. They are basically feature engineers, re-engineering a basically new, more nuanced, more useful features each time, right? Then linear separability can emerge after transformation. So when you think about the exclusive OR problem, we now solve it. We can solve the exclusive OR problem by introducing one or two hidden layers. And we're going to do that on Thursday when we do a bit of hands-on with 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 PyTorch, right? So the intuition here is that the first layer will create the intermediate features. Remember, I said feature engineering. So the first layer, the first hidden layer, the first hidden layer is not the input layer. So the first hidden layer is going to create some intermediate features. Then the second hidden layer is going to combine these intermediate features, right? Doing additional feature engineering to combine them into separate classes. So with just two hidden layers, you can solve the exclusive OR problem, right? Yes. So the question is, if we have multiple hidden layers, at which of them? At all of them. Every layer re-engineers the features. But the interesting is that it re-engineers the features to be better and better. It's better and better re-engineering. Each successive layer, right, will re-engineer. Basically, that's what the layers are doing, right? They're basically re-engineering. If you think of features as the individual inputs into a layer of a neural network, right? Then the next layer is getting another one. but it is getting it from a layer that has been trained, because you are training these models, right? You are modifying the parameters. Okay. So what is happening essentially is that as you know, you continue to train, the models get better at the feature engineering. So it's kind of terminology, right? It is kind of an easy way of me making it, you know, understandable, right? So that's what the hidden layers do. Then the activation functions now add their own magic, right? And the magic that they're adding is they introduce the non-linearities that allow the input space to be bent and folded and reshaped in such a way that the linear combination can now be projected into a hyperplane. So basically, right, there are multiple ways you can look at this thing. You can look at it as, you know, the artificial layers are basically bending the surfaces, the input space, in such a way that the linear functions, which is the linear combination of the weights and the input, is able to cut through it, right? And you are able to get very tight decision boundaries, non-linear decision, complex decision boundaries. Okay. All right. There's a question, what's the difference between ANN and CNN? ANN is a generic name for all of them. Every neural network is an ANN. It's an artificial neural network. Like I said, in the old days, there was a lot of emphasis on the artificial part to differentiate it from the human biological neural network. But these days, nobody really calls neural networks artificial neural networks anymore, because once it's a modern concept, everybody understands it. So once it is a neural network, we know we are talking about artificial neural networks, right? A CNN is a convolutional neural network. It's a specific architecture or type of neural network that is optimized for vision and is based on the concept of a convolution. A convolution is a space invariant transformation of inputs, right, in an input space. We're going to look at it next, right? Okay, so then the output layer. So we've talked about input layer. We talked about the hidden layers. There can be multiple hidden layers. There can only be one layer and one output layer, but you can have any number of hidden layers. So any layers in between the input layer and the output are called hidden layers. So the role of the output layer is just to condition the final output so that it will be what, you know, you are training the model to be, right? Or it will predict. Basically, it's what you use to condition the output to match the target values. Okay. So, like we said, if you are predicting probability, then your output neuron or output layer rather should have sigmoid if it is a binary classification, right? If it's a multi-class, you know, classification, then you have n number of neurons, where n is the number of classes in your category, and you use softmax. So we'll look at some of those later on. But if you are doing a regression problem where you are trying to predict an exact number, an exact value, rather than a classification, whether it is here or there, but an exact value like 3.625, then you will not do an activation, because an activation is going to introduce a non-linearity. In the context of an output layer, you don't want that non-linearity. You want the exact value to come out, right? So the key characteristics, the number of neurons on the output layer depends on the task. So if you are going to do a classification that is only true or false, you will have only one neuron in the output layer, because that one neuron can then be trained to give you a value of 1 if it is true, and a value of 0 if it is false. But if you are trying to do a multi-category or multi-class classification, then you will want to do a probability distribution. We'll call it probability distribution, which is done with a softmax activation, right? And you have to have the number of neurons to match the number of classes in that category, so that each neuron will output the probability that the class it represents is true, right? That is a multi-class. Then for a regression problem, if you have a single output, you have a single, if you want just a single value, you want to predict only a single value, then you have a single neuron. If you want to predict multiple values, then you have n number of neurons that match the number of values. And the main thing is that, yeah, like I said, activation function is task dependent, and the output has to be interpretable. Unlike the value from the output in the hidden layers that can, you will not be able to interpret it. It will just be numbers that you cannot know what they mean, right? But the value from the output layer, from the neurons on the output layer, have to mean something. It has to match the training target. Okay. So this is kind of looking at it. So this is like a model, the output layer, you are training it to model a prediction, whether something is true or false. And you see that there's just a single neuron on the output layer, right? And we're using a sigmoid function because a probability distribution, sorry, a probability of 0 to 1 that we want to predict. And if it gives you a probability of 0.24, then we can now use a threshold, like when we're doing a logistic regression. We now use a threshold and say if it's above 0.5, we'll take it as true. Below 0.5, we'll take it as false. Okay. So now, can we have more than one neuron for regression? Yes, you can if you are doing regression on multiple values. So for example, you could actually train a neural network to predict price of, to predict multiple regression things, right? So for example, we want to predict the price of housing, right? You also want to predict maybe how long that house will last. And then you want to also, things like that, but it should be kind of correlated. Then you would have a single neuron output to give you the predicted price. You have another single output, regression output, to give you a prediction of maybe how long that house will last before it needs maintenance and all of that. So you can have, it's all task dependent. So that is kind of summary of that. And every neural network has those basics, right? Input, hidden, output layers. Now, the architecture part of it is like, okay, how do we do the hidden? Because like we said, the output and the input depend on the input depends on the data that's coming in. The output depends on the training target that you want to predict. The hidden is now where you have flexibility to bring whatever architectural implementations and changes you want, right? And we'll talk about that. But the first thing I want to talk about is the most basic and fundamental kind of layer is what we call a fully connected or dense layer. So a fully connected or dense layer is a layer where all the neurons are connected to all the inputs, right? So you can see this one now. In a fully connected layer, you see um, this yellow is a hidden layer, right? Typically, a hidden layer would have more neurons because you want to generate more new features. Then this blue would be the input layers. Now, each input layer is connected to each hidden layer, right? So there are a total of 4 times 3 connections. There are four neurons in the hidden layer, and there are 3 neurons in the input layer. So the total connections or weights is 4 times 3, that is 12, right? And that will be the number of parameters. You say that there are 12 parameters. Well, you have to add the biases. Each of the hidden layers will also have a bias. So that's 4. So 4 times 3, 12 plus 4, that's 16. So that's the total number of parameters in this neural network, right? But you see that every input is connected to every hidden layer neuron. That's what it means by fully connected. Each is fully connected to the other, or it's called a dense layer. Some terminology is called a dense layer. So whenever you hear fully connected layer, like FC layer or dense layer, it means the same thing. Every input is connected to every neuron in that layer, right? Then you have sparsely connected, like this one. You can see in this case, not every input that is connected though. You have like this one is connected here and here, but it's not connected to this other two. This one is connected to only one here, but it's not connected to the other 3. This one is only connected to 3, right? 1, 2, 3, but it's not connected to this. So it's not a dense layer or a fully connected layer, right? It's a sparsely connected layer or a sparse layer. So this layer will be called a sparse layer. So by the way, in this context, the layer is the one that is receiving the connections, not the one that is sending the connection. So this would not be called a densely connected layer if its own inputs were not dense. So for example, if this one is another layer and it is only one to one like this, right? This layer here is not densely connected. Rather, it is this layer that is densely connected. So the densely connected, the name of that always refers to the layer that is receiving the connection. That is, the signals are going, you know, into that layer, right? Not the other way around. Okay. So the mathematical form of a densely connected layer is what we did the same thing. It's basically the same thing, right? The weight of this layer, right, times the activations of the previous layer. So remember, A is the activation of a previous layer, which is the input of the next layer or the current layer. The activation of a previous layer is the weight of, sorry, is the input of the current layer. I'm repeating that so that it is clear. So when you see A actually means the output or activation of the previous layer. And W is the weight that connects that previous layer to the current layer, right? And determines how much of that activation, how much of that signal from the previous layer is getting to each of the neurons, right? And then of course the B is the bias. So that's why you see this is L minus 1 because it is the layer before it. So this is the weight of the current layer. So basically the mathematical form of a fully connected layer is the Z. Remember the Z is the intermediate output before it goes into the activation function. So, but when it goes through the activation function, it becomes either A, which is the activation of that layer, or Y hat, or Y rather, Y. But we don't use Y hat. We don't use Y or Y hat in neural networks unless it is in the output layer, because the output layer is the one that directly relates to the Y, which is the true value or the value you are trying to predict. So we typically only use Y as an output, sorry, as a symbol for the output in the output layer. But in the intermediate hidden layers, we typically use A because it hasn't yet gotten to the point where we want to, where the Y is, which is what we're trying to predict. So anyway, um, so this basically says that the intermediate output, right? The combination of the linear combination, right, of this particular layer, ZL, equals the weight of this same particular layer, WL, times, this is a dot function. If you go back to logistic regression, I talked about vectorization and all of that. But the A is the output of the previous layer. That's why it's L minus 1, the layer before. And then plus the bias of this current layer. So this is the formulation for a fully connected layer. In fact, basically the formulation for any layer, right? The only thing that is in the sparsely connected layer, we can simplify everything by saying some of the weights are 0. A sparsely connected layer is basically a layer where some of the weights are 0 because it means no signal. More layers until later on when we start doing stuff with PyTorch. So we will now put all that we have done together. There is still a whole bunch of stuff here. Maybe let's see how much of this I can do and then maybe do a recap when we meet because we already passed time. But yeah, so when you put all of them together, you have what we call a feed-forward neural network. A feed-forward neural network is basically a neural network that the information feeds forward, right? That's basically what it means. So in a feed-forward neural network, data flows in only one direction, as opposed to a recurrent neural network where the data can cycle back, right? There are no cycles or feedback loops, and each layer fits into the next. So the typical structure is always you have the input layer, then you have multiple hidden layers, right? Then you have the output layer. So this is just a typical, drawing of it. So you have the input layer, right? X1, X2, X3 that come in, and then you have this fully connected layer here, which is a hidden layer. It's fully connected. You can see each of the inputs is connected to each of the neurons on the hidden layer, right? And then the neurons on the hidden layer also now each of them connect to the output layer. The output layer has only a single neuron because we're only trying to predict a single value, right? And then those outputs come out there, and the output is y hat, right? So the output, the actual output is y. The output you are predicting is y hat, and you're always going to calculate the error between the y and y hat, and that will give you the cost. You take a gradient of that cost function, you back propagate that gradient through here, and then you update the weights. So we are going to look at how to do that on Thursday. Now, so that's for propagation. What I just described, input enters the network. Each layer applies a linear transformation, which is the linear combination of the inputs through the weights, the summation xiwi, right, plus the beta, sorry, plus the bias. And then it passes that linear combination, which is Z, passes through the activation function. And then that activation function for each layer. So when we say each layer now, we are talking about all the neurons in the layer at once. We are seeing it as a single unit. And this is one thing that you need the transition mentally in your mental model. You need to transition from thinking of a layer as a set of neurons, but as a single unit that is, yeah, made up of neurons. But each of those neurons, like we said, is doing its thing independently. It's all in parallel. Okay. That output is produced, and that output the output that comes from a layer is directly equal to the size of that output is directly equal to the number of neurons in that layer. Okay. So that's a feed forward. And this is kind of an animation that will show how this happens. So this is the input, right? This is the input layer, and then you have this hidden layer which has a couple of neurons. So you now see that each input sends signals to each neuron. Even though this is showing it sequentially, right? But it's kind of trying to correlate it with this matrix. We are going to talk about this later on, how we will now decompose the interaction between two layers into a matrix dot product. That's basically what it is. The summation xiwi is a dot. Well, we've seen it already. It's a dot product, and that's what it is, and that's what it's being represented here. A dot product. This matrix here is the matrix of the weights. So remember the number of weights is the number of inputs, right, times the number of neurons in the next layer or in that layer. So you see that number of inputs will be rows and the number of neurons will be columns. And then this is a vector that represents the inputs, the actual input, right? The number of inputs. So you do that vector calculation and you're going to get another vector that comes out. That vector represents the output from from this layer. So that is forward propagation. We're going to look at it in detail, but you will see that at the end of the day, it can be summarized with this equation Z, which is the linear transformation, the intermediate output, is W dot X, a dot product of the weight and the input plus the bias, right? And then we now apply this Z into the activation function F, and we'll get the activation A, which is also the output from that layer, right? And then this just keeps happening across each layer until you get to the last layer. So if there are 100 layers, that means this will happen 100 times, right? And then the last one will go to the output layer. If there are 1,000 layers, it will happen 1,000 times and so on. And this is a simple principle of deep neural networks. So the key idea here is that forward propagation is a prediction step of a network. So that's how neural networks predict, basically forwarding the signals forward. The signals flow forward from input to output. There are no feedback loops. That's why it's called a forward propagation. And this is just another way of representing the same thing. It's the same thing. This is now a mathematical formulation, which I had already provided, where Z for each layer is the weight of that layer times the activation coming in from the previous layer, plus the bias in that layer, right? That Z is the intermediate output, which is the linear combination of the inputs through the weights. And then you take that linear combination, you pass it through the activation function F, and you get the activation for that layer. And that activation for that layer will become the input for the next layer. And this will just keep cycling like that until you do all the layers. And this is also represented with this animation. And at the end of the day, you get the output layer, it comes out. You now calculate the error. The output layer, the A of the output layer is also the Y hat, because the activation or the value that comes out from the output layer is what you are training it to predict. So it basically becomes y hat. So the error is y hat minus y. Yeah, that's what is said here, that for the output layer, the y hat equals the activation for that output layer. Okay, so this is again the same thing. It is so important that I put it on 3 different slides in 3 different ways, but it's essentially the same thing. Again, the combination of the linear combination of each layer plus bias and the input from a previous layer gives you the Z, right? The Z, you pass it through. Here, they now specify the activation function here to be a ReLU. So you pass it through a ReLU, and that gives you the activation of that layer A, right? The activation of that layer A becomes the input of the next layer, right? And at the end of the day, when it gets to the output, the activation of this layer is multiplied to the weight of the output layer plus the bias of the output layer. And that gives you the Z of the output layer. And the Z of that output layer, we pass it through a sigmoid function because we are doing a binary classification or probability, classification output. And that becomes a Y hat. So again, this one is now simply here, input layer X1, X2. You have a hidden layer which passes through a ReLU activation function, and then you have an output layer which passes through a sigmoid activation function. Right. So I'm going to pause here because I think there's a lot of information that has gone, and we have kind of run out of time. When we come back, we will talk about. We already talked about loss functions, so this is more of a recap, right? A loss function is basically how you calculate the difference between what you want it to predict and what it's actually predicting. And then you use the loss function as a basis to calculate the gradient. And then you use the gradient as a basis to calculate how much you modify each parameter. So every single parameter, every single weight in the neurons or in the layers will be modified. That's why neural networks are so powerful. If you have a neural network that has a million parameters, you will have to calculate the gradient for each of those parameters. And then you have to apply the learning rate and then modify those parameters, you know, the same way. So we will start with the loss functions. It's going to be a recap. We already know this, For neural networks, we typically will use a mean square error loss function, right? Unless we want to do binary cross entropy, in which case we use a binary cross entropy, which we've already looked at. Or if we want to do a multi-class categorization, then we use a categorical cross entropy where the classes are more than one, or sorry, more than two, right? It's more than true or false, right? You want to say, okay, it's what? Blue, red, yellow, green, and all of that. Then we will talk about backpropagation. Backpropagation is a whole deal on its own, and we'll talk about a bit of historical, and then we will look at backpropagation. So there's this animation where we're now taking the gradient and we are sending it backwards to modify the parameters. So backpropagation is a phase where you modify the parameters, just like we're doing it when we're doing gradient descent. So essentially, that's what we're doing here. It's a gradient descent, and we'll talk about the fact that neural networks only became useful when backpropagation was discovered. It is not the first day that neural networks were discovered that backpropagation was discovered. So yeah, we will look at that. And then we'll do a bit of hands-on with TensorFlow. So let me pause, let me stop at forward propagation for today. I'll take any questions if there are any questions. If not, we'll meet on Thursday. We'll round up the backpropagation. There's a whole bunch of stuff for us to do on PyTorch. I will have to do an introduction to PyTorch, and then also what I would advise. Well, okay, it's not going to be really difficult to do PyTorch in your Colab, so we'll still do on Colab for now, and we can use PyTorch just to do a few things. We're not going to use TensorFlow or any other one, mainly because TensorFlow, even though right now there are a lot of models that have been built and trained with TensorFlow, but TensorFlow is slowly being phased out. Even Google are the ones that started off TensorFlow, but they are slowly phasing it out. And it will get to a point where they will not really use it again. Google are kind of moving from TensorFlow to JAX. JAX is much better, it's more modern, TensorFlow was in the old days. It has a lot of issues now, a lot of limitations. It uses a graph approach and all of that. I'm not going to go into all the details. Um, so that's it. Any questions? So I have a couple here. What is the best way to understand PyTorch and TensorFlow? I also used to see Torch and Tensor. Yeah, PyTorch is just a framework that helps you to build neural networks much better, much faster, without you having to do all the maths by yourself. Because without PyTorch, you would be doing all of this back propagation. But PyTorch has this very powerful feature that takes away a lot of pain from this process of training neural networks, what they call autograd. Autograd is a feature where PyTorch can automatically calculate the gradient of every function. You can even define a function in your code, and PyTorch will automatically calculate the gradient. So when you're doing back propagation, you don't need to manually come up, figure out what the gradient equation is. I would have liked to do that, but I don't know if I have enough time, to put everyone through your paces and give you a little bit of pain doing back propagation by hand. That shows when you are able to do back propagation by hand, then you know you are a machine learning expert. So I always try to do that, calculate. I will do that, right? I'll do that, but for a very simple, tiny model that's not complex, with a simple activation function that is easy to differentiate. Because for you to do back propagation, you need to be able to calculate gradient. So your every function needs to be differentiable, right? And that's what we now talk about differentiable functions. Okay. I don't know why people are saying sorry. I said I want to put you people through pain, and you're saying sorry. All right, that's it. That's it. Okay, so I'll stop the recording.